Hello, I'm Mr. McBrien. This is TJ20, Circuits 2, Basic Circuits. Yesterday we talked about the guess system for reporting mathematical problem solving, and we talked about power in a circuit. Today I'd like us to move our way through some definitions of electricity and talk about a very important law called Ohm's law. Okay, so let's start with the question, what's electricity? I'd invite you to pause the movie and think for a second about what your definition of electricity is. And then we'll see if we can compare it with some accepted ideas. Okay, let's start with a definition of static electricity. Now, static electricity, you might know that this is the electricity that appears when you say rub a balloon and static electricity builds up on it. It's the electricity that on a dry day, if you walk across a carpet, you may feel a small zap when you go close to someone else. Static electricity is an excess of charge on an object. And like the name implies, static electricity doesn't move. It's measured in coulombs, and you won't be responsible for this definition, but a coulomb is equivalent to the charge of approximately, well, this huge number of protons. Alright, and static electricity is neat, and it's very interesting for certain experiments, but to be honest, electricity when it moves is much more interesting and much more useful. We call electricity in motion current. What is current precisely? Well, it's the speed at which electricity moves. It's measured in amperes, and the definition of ampere is just a coulomb per second. Usually, we show current as an arrow from the positive part of a circuit to the negative part of a circuit. So when we close a switch like this one, current starts to flow because of the potential that's there. We'll get to this in a minute. And current flows from the positive part of the circuit to the negative part of the circuit. Alright, so it moves. Through what does it move? Well, current moves through a circuit, and a circuit, almost by definition, has to contain a potential source, like a battery, a conductor, typically wires, and a load, like this light bulb shown here. So if you are asked, what are the components of a circuit, of a basic circuit, you can simply answer a potential source, conductor, and a load. Okay, so that potential source, potential difference. There has to be some kind of, to have movement, we have to have something to push the things that move. And in a standard circuit, that would be the battery or the power supply that does so. The force that pushes the electrons through the circuit is called the potential difference, or the potential, and units of potential are volts. When we apply that potential, we'll often say we're applying a voltage, but more correctly, we're applying a potential difference across. And the symbol for a battery is simply this representation of a long line representing a positive terminal of a cell, a short line, the negative terminal of a cell, and repeating that to represent multiple cells. So the positive and negative that are shown on here are actually unnecessary and are often left out. That's because the long line is the positive. All right, so resistance. Any circuit, other than a short circuit that we'll talk about briefly in a minute, any circuit will resist the flow of electricity. And the component that does this resisting, that contributes the resistance, is often called the load. And that resistance is often based on work done by the device. So it could be a motor, like a fan motor, or the load could be just based on the type of material. And so resistors, rather than doing work, the material itself resists the flow of electricity. We measure resistance in ohms, and the symbol is the Greek letter omega. The symbol for a resistor, there are a couple of accepted ones. This is the one we'll use in TIJ, representing a coil of wire. Okay, I alluded to short circuits a second ago. Any circuit that doesn't have a load will allow electricity to flow through unrestricted. It won't slow down. And there are lots of reasons why this circuit without a load is a bad idea. One reason is that most components in circuits have maximum current ratings, and if we exceed these, they'll burn out. Another reason is that batteries have a certain current level that they can support, and if that's exceeded, they'll heat up too much. The chemical process that produces the potential difference will go too fast, will generate too much heat, and the battery can explode or burst into flame. And a quick internet search dug up this photo of a house that they claimed the fire was due to a 9-volt battery stored in a junk drawer that connected up the two poles. It was a short circuit. There was a potential difference without a load. So that leads us to a very important rule in this classroom. Never connect the positive and negative terminals of a battery without a load in place. That short circuit can be dangerous at best. Okay, so let's get to something a little more quantitative about circuits. Ohm's law is a description of the relationship between current, potential, and resistance. And it's a pretty simple expression. The current is equal to the voltage divided by the resistance. No great shock. If you'll pardon the pun. So the current goes up when the voltage goes up. So when the potential difference goes up, the current goes up. And when the resistance goes up, the current goes down. So that's very well represented by Ohm's law, I equals V over R. And this is a key component to a lot of what we're going to cover through the next 3 weeks. So applying Ohm's law, what it means is we can do things like this. We can take a known resistance and a known potential difference, and we can calculate the current we can expect. So this question, what's the current in a circuit with a 200 ohm resistor and a 9-volt battery? So let's use our guess approach. Given the potential difference is 9 volts, the resistance is 200 ohms. The unknown is the current, I. Our equation, I equals V over R. Substitution, I equals 9 over 200, which by my math comes out to 0.045 amperes. And we're not quite done. That's our solution, but we need to ask ourselves the two questions. First off, we've got current. The units are amperes, so our units look good. Amps are, of course, are units of current. And does our answer make sense? Well, we're starting to get a little bit of a feel for amps, but it's going to take some time. For right now, we can say that's a pretty low current. Well, all right, and a reasonable current. So we'll underline it and move on. Okay, calculating current with voltage and resistance we've already done. Calculating voltage we can also do, of course. So what voltage is required to get 0.02 amps of current with a 1000 ohm resistor? Our given this time is our current and our resistance. Our unknown is the voltage. Equation, I equals V over R. Oh, wait a second, it's not in the right form, right? We need the voltage on the left-hand side. And so some quick algebra sees that to get voltage alone, we need to multiply both sides by resistance and get V equals IR. Substitute in 0.02 amps, 1000 ohms, and the solution, 20 volts. But we're not quite done. The two questions, well, it said what voltage, what potential. The units of potential are volts. Very good. So we've got V for volts. And 200 volts is, 20 volts is a reasonable amount. That's a pretty high potential, but there are 24 volt batteries. So certainly we could say that this is a somewhat reasonable value. So we can underline this and move on. All right, one more. Why not? We can calculate the resistance. If a 12 volt battery gives us 0.1 amps of current, what's the resistance in the circuit? Again, we state our given, our current and our voltage. We then know our unknown is the resistance. The equation I equals V over R. Oops, not in the right form again. We need to get R on its own. So some quick algebra converts that to R equals V over I. Substitute in 12 volts divided by 0.1 amps. And our solution, 120 ohms. Well, okay, time for the two questions. Ohms are the units of resistance, so that's good. 120 ohms, well, we've seen resistors of this amount. That seems somewhat reasonable. Okay, R equals 120 ohms. Okay, let's sum up. Potential is the force that pushes electrons through a circuit, and we measure potential or potential difference in volts. Current's the speed of movement of electrons through the circuit, measured in amperes. And the difficulty that electrons encounter when they're moving through the circuit is the resistance, measured in ohms. Ohm's law states that the product of the current and the resistance is the potential, V equals IR, or I equals V over R. For your homework, please go through the Ohm's law worksheet. And for those of you who are interested in something maybe a bit more challenging, here's an extension question for you. Go online and research the resistance of a given piece of wire. It'll typically be given in ohms per foot or ohms per meter. Then what I'd like you to do is calculate the current you can expect if you connect the terminals of a 9-volt battery using a 20 centimeter piece of this wire. And I think this will give you some insights as to the things that we've discussed today. Thank you very much, and have a great day.